Imagine, if you can, the universe in its infancy. Envision a cosmos without stars, without galaxies, without even the quiet glow of a distant nebula. Instead, picture an endless, blinding fog, an ocean of searing energy, hotter than the heart of any star today. There is no up, no down, no night or day. Across this primordial sea, light itself is trapped, imprisoned by the unruly swarm of particles that fill all of space. The world is opaque, the universe blind. For 400,000 years after the Big Bang, this is the state of everything that ever was. We sometimes call it the photon era, for light, or more precisely photons, are everywhere. But paradoxically, not an inch of that light can truly shine. Instead, each photon is born free, but immediately runs into a chaos of electrons and protons, tiny charged particles that thrive in the universe's furnace heat. At every turn, photons are scattered, absorbed, redirected, their journey halted after the smallest fraction of a millimeter. The cosmos is like the thickest fog multiplied by infinity, so dense that not even a beam of light could pierce it. In this early epoch, the universe is a churning plasma, a state familiar to us today, mostly in the heart of stars or the brief flash of lightning on Earth. But imagine the entire cosmos as a single, boundless star. Temperatures soar above 10,000 degrees Kelvin. Hydrogen, the simplest and most plentiful element, cannot yet exist in its neutral form. Atoms are stripped naked, protons and electrons racing independently through the firestorm. Every time a photon tries to go anywhere, it crashes into a free electron and bounces off in some random direction. It is like being lost in a perpetually illuminated but utterly featureless cloud, with no landmarks, no horizon, only pure, undiluted brightness, utterly hidden. For hundreds of millennia, this is all there is. Time marches forward, but very slowly, the universe begins to change. The Big Bang, that initial incomprehensible explosion, set space itself expanding, an expansion that continues to this very moment. As the universe grows, it cools. The temperature, so impossibly high at the beginning, begins to fall. The seething plasma thins, the energy spreads out, and the relentless violence of those early years gradually abates. By the time 300,000 years have passed, the temperature has dipped below 3,000 Kelvin, still hotter than the surface of our sun, but no longer able to keep electrons and protons apart with such ferocious efficiency. A crucial threshold is crossed. Slowly, inexorably, a new process begins. Protons, positively charged and yearning for balance, begin to capture electrons, each a tiny, negatively charged companion. When this happens, the result is a neutral hydrogen atom, stable, whole, and capable of quietly existing without immediately falling apart. This period is known as recombination, though it might more accurately be called combination, for these particles have not united before. At last, the universe is cool enough for atoms to be born, and with neutral atoms replacing the charged plasma, everything changes for the photons. With far fewer free electrons to scatter off, the photons are finally free. No longer are they doomed to stumble blindly through a maze of obstacles. They can travel vast distances across the entire width of the universe without being absorbed or deflected. It is as if, after an eternity of blindness, the cosmic fog clears overnight. For the first time, the universe becomes truly transparent. Light, in the profoundest sense, is born. This moment is one of the most significant in all of cosmic history. The photons that slipped free in this dawn have been traveling the universe ever since, older than any star, any planet, older even than the atoms in your bones. They are ancient messengers, bearing the story of their origin across billions upon billions of years. We still see them today. In the late 20th century, scientists built instruments sensitive enough to detect these primeval photons, now stretched by time and cosmic expansion into the microwave region of the electromagnetic spectrum. Where once they were blazing visible light, they are now a faint, cold whisper, detectable only by the most carefully designed telescopes. This is the cosmic microwave background, or CMB, a subtle afterglow that fills the universe evenly, coming at us from every direction. For a long time, its presence was merely a brilliant prediction, the inevitable outcome of the hot Big Bang model. But in 1965, a pair of radio engineers named Arno Penzias and Robert Wilson, scanning the skies for unrelated purposes, stumbled upon a persistent hum, an ever-present hiss coming from all corners of the sky, stronger and steadier than any known source of interference. What they had discovered was nothing less than the echo of creation, the light from the liberation of the photons, stretched thin by cosmic expansion, still glowing softly after nearly 14 billion years. And there, in that background glow, lies one of the greatest treasures of science, the oldest light we can ever perceive. To this day, satellites such as COBE, WMAP, and Planck have mapped the CMB in exquisite detail, revealing that it is not perfectly smooth, but minutely uneven. Tiny, almost unimaginably small fluctuations in its temperature fill the sky, amounting to differences of just 1 part in 100,000. But these slight imperfections are no accident, no mere noise. Rather, they are the seeds from which all the structure in the universe would eventually grow. The blueprints for stars, galaxies, clusters, and the great cosmic web. Places where the radiation was slightly warmer mark regions of higher density, a bit more matter and energy, tugging on everything around them, with a little extra gravitational pull. Over time, these seeds would grow, attracting more and more, eventually forming the vast structures we observe populating the cosmos today. By analyzing the cosmic microwave background, we can deduce the age of the universe, now estimated at about 13.8 billion years. We can infer its precise shape and curvature, whether it's flat, closed, or open, by subtle patterns in the background's glow. Even the amount of dark matter and dark energy, two of the universe's greatest mysteries, make their presence felt in the CMB's fine detail. At the heart of it all are sound waves, acoustic oscillations that rippled through the early universe. In the hot, dense plasma before recombination, pressure waves would propagate, driven by the interplay of gravity pulling matter together and the intense radiation pressure pushing it apart. The result, a cosmic symphony, oscillating back and forth, imprinting subtle rings of density into the primordial plasma. Today, these ripples echo in the CMB as faint, regular patterns, baryon acoustic oscillations, the fossilized relics of sound waves that once boomed through the baby universe. If our eyes could see microwaves, the sky would be awash with this ancient light. Look in any direction, and a faint, fuzzy orange bubble would envelop us, the universe's baby picture, a remnant from the epoch when atoms first formed and photons escaped. That light is the oldest we can ever hope to see, its age nearly equal to the universe itself. In the aftermath of recombination, with light freed at last, the universe entered its next phase, the Dark Ages. The cosmic fog had lifted, but stars had yet to ignite. For millions of years, the night sky would remain empty, no new sources of light breaking the darkness. It was an era of calm before the next great storm, an epoch of chilling silence as matter cooled and settled, coalescing under gravity's patient hand, preparing the stage for the first fireballs of starlight. And yet, those ancient photons from the cosmic microwave background still journey on, undisturbed, crossing space and eons alike. Some of them, incredibly, even reach us, caught by delicate satellites, recorded by careful scientists, and transformed into maps that tell us about the universe as it once was. To reflect on this story is to realize just how intimately connected we are to the first light. The photons that fall today onto sensitive detectors, or even those that pass quietly through our own bodies, have spent nearly 14 billion years crossing a changing, expanding universe. They have witnessed the entire span of cosmic history, the formation of galaxies, the birth and death of stars, the emergence of life and conscious thought. We, in a sense, are witnesses too, for in looking out into the universe, in mapping the cosmic microwave background, we are gazing not only at the past, but at the very moment when the universe became visible, when, after ages of opacity, the curtain was drawn back and light took its first free flight. Consider what science has revealed about this earliest epoch. The story begins with the unfathomably dense, energetic chaos of the newborn universe, a place where temperature and pressure were so extreme that atoms could not survive, where energy and matter blended in a primordial fire. As space swelled, those energies began to spread out, and with each passing millennia, the universe cooled. It did not cool gently or quickly, but over hundreds of thousands of years, the relentless expansion gradually lowered the temperature enough for quantum transitions to occur. When the temperature finally dropped below 3000 Kelvin, protons began to capture electrons with increasing frequency. This was not like flipping a switch. It was a staggered, statistical dance, with atoms forming wherever the conditions allowed. Once enough neutral atoms populated the cosmos, the cage of the photon was broken. The cosmic microwave background is, in a very real way, a snapshot of that precise moment, the instant the universe became transparent. Each tiny patch of the CMB corresponds to a region of the early universe, frozen in time. When we look at it, we are not merely seeing a relic, we are seeing the universe as it was, as it essentially became what we now know. For history, the CMB is a Rosetta Stone. It is remarkably uniform, confirming that in those ever so early years, the cosmos was nearly featureless, but not quite. The faint ripples, those delicate fluctuations in temperature, encode information about the earliest stages of the universe. They help us test the theories of cosmic inflation, the idea that the universe ballooned from subatomic size to astronomical expanse in less than a heartbeat. They teach us about the distribution of matter and energy, about the very geometry of space and time. More than that, the subtle fingerprints of the CMB have revealed things we never expected. From its study, astronomers have deduced the presence and proportion of dark matter, an invisible form of mass that holds galaxies together, but reveals itself only by its gravitational pull. Dark energy, stranger still, shows its effect in the way the expansion of the universe accelerates, an outcome first glimpsed through the careful mapping of the background radiation. The acoustic ripples fossilized in the CMB map, the baryon acoustic oscillations, are crucial as well. These pressure waves, propagating through the plasma, serve as a kind of cosmic ruler. Their characteristic size, as imprinted in the CMB, allows astronomers to measure the scale of the cosmos itself. To see these echoes is to hear, in silence, the reverberations of the universe's first grand symphony. If our senses could be tuned to microwaves, each patch of sky would shine with this ancient radiation, and no constellation, no star, no familiar galaxy would break its uniform glow. We would see not the world of today, but an all-encompassing, featureless afterglow, a living fossil, glowing faintly in hues of orange and red, an unending bubble around us. And yet, within that gentle glow, we could discern subtle patterns, the very hints of form and destiny. Astonishing, too, is its age. After nearly 14 billion years, those photons are still sailing ceaselessly through space. They are the oldest messengers we will ever encounter. No telescope, no matter how powerful, can look back before this moment of recombination. Earlier still, the cosmos was closed to sight, its secrets locked away in that blinding plasma. But with freedom came opportunity. Once the universe was transparent, the seeds of structure, the minute differences encoded in the CMB, could begin to grow. Gravity slowly gathered the slightly denser regions together, drawing in more matter, while the slightly emptier regions grew emptier still. Over millions, then billions of years, these primordial differences gave rise to everything. Stars, galaxies, clusters, and the boundless cosmic web that spans creation. Yet, for hundreds of millions of years after recombination, there were still no stars. The universe entered the Dark Ages, a long, chilling interval in which the fog had cleared, but illumination had not yet begun. The light of the CMB traveled freely, but all else was darkness. Gas cooled and clumped, and slowly, silently, the precursors of galaxies and stars gathered in the void. When dawn finally returned, it would be with the first stars, their birth lighting up the vast night, their radiance marking the true dawn of complexity in the universe. But even then, the story of those first photons continues. Some will be engulfed by new clouds of gas, others captured by newly forming stars. But untold trillions will keep traveling, never again to be trapped, echoing their message across time and space. The universe, once so opaque, became clear, its architecture revealed in the ghostly glow of the background radiation. Every measurement, every map, every theory that tries to probe the deepest questions of cosmology returns, in some way, to the CMB. This faint whisper of ancient light is the key to our history, our origins, and our place in the grand story of existence. When we gaze up at the sky, most of what we see is merely the nearby surface, stars of our own galaxy, perhaps a few distant clouds in the Milky Way, and for the most acute eyes or telescopes, the faint smudge of Andromeda. But under it all, filling every direction, is the unending echo of the universe's emancipation, the cosmic microwave background, a nightly reminder of the first moment when the cosmos let itself be seen. And in the ultimate humility, we recognize that while our own lifespan is a blink, while our civilization is new and our instruments young, the light that tells us this story has traveled uninterrupted for almost 14 billion years. Through all the changing eons, across the birth and death of stars, past the slow assembling of galaxies, beyond the rise and fall of everything we know, those photons endure, a message from the beginning. So when you contemplate the first 400,000 years, recall this. The universe began not in darkness, but in blindness. Its light was bound, its vision shrouded. Yet through the slow, relentless working of physics and time, the shroud was lifted. Some of those photons, liberated so long ago, are still crossing space, touching satellites, scientists, and even, perhaps, brushing your skin at this very moment. Tomorrow, the next great story will unfold, the awakening of the universe as the first stars ignite, banishing the darkness and setting the cosmos on its path to complexity. But always, behind and beneath every new light, the ancient photons sing, a reminder that in the very first hours, the universe broke its bonds and let itself be seen, setting the stage for everything that would follow.